Hello, calculus students. Welcome to our 7.1 notes. We're going to learn how to find the area between two curves in a plane. So already this year we've talked about the idea of the concept of a definite integral representing the area of a region under a curve. So what we're going to do in this lesson is we're going to extend that idea to include the idea of the region between two curves on a closed interval from A to B. So for example, if you take a look at this picture, we have a function f, we have a function g, we're looking at their graphs, and we're going to learn in this lesson how to find this area between the two curves from A to B. So let's think about this, what's going on both graphically and analytically. So if you take a look at this picture, if we look at the region under the curve from A to B that's just under F, that would be this region right here, okay, under the graph of F from A to B. Now, how would we express that analytically? We would express it as an integral. We would say the integral from A to B of f of x dx. Now, what we're going to do is now take a look at the region under the curve just under G. That would be this region. Again, that's going from A to B. So how would we express that analytically? We would say the integral from A to B of g of x dx. All right, now, if we were to subtract those two integrals, what we're doing then is we are taking this green area and subtracting this yellow area from it, and what that leaves is this area right here. Let me shade that in as well. That leaves this area. So in other words, how we would express that analytically is we would say the integral from a to b of f of x dx minus the integral from a to b of g of x dx is equal to the integral from a to b of, let's start some brackets and say f of x minus g of x, close those brackets, dx. All right, so in other words, let's just kind of state this property formally. If f and g are continuous functions on a closed interval from a to b, and g of x is less than or equal to f of x for all x in that closed interval, then the area of the region bounded by f and g and the vertical lines x equals a and x equals b is given again by this. It'd be the integral from a to b of, start some brackets, f of x minus g of x dx. All right, so let's take a look at some intervals. Let's take a look at some examples and see how this works. So example 1 says, let me get it straight, there we go, says, find the area between the two non-intersecting curves on the closed interval. So what we're looking at, it describes right here, it's the region bounded by the graph of f, all right, the graph of g, and then the vertical lines x equals 0 and x equals 1, which is this line, okay? So first of all, I just want to point out, you'll see in these pictures, these little rectangles. Now, this is what we call a representative rectangle. And the reason why it is there is to remind us that how we defined integration to begin with. Do you remember when we did Riemann sums and we looked at a whole bunch of rectangles? In fact, I could draw several rectangles, and we talked about how if I had more and more rectangles and they got thinner and thinner and thinner, then the sum of the areas of those rectangles would get closer and closer to the area of this shaded region, okay? So if we took the limit as n approaches infinity of n rectangles, then the sum of those rectangles would be the same as the shaded region. So you'll see these rectangles. They're just called representative rectangles to remind you that an integral is the sum of an infinite number of rectangles. Okay. So what we're going to do to find this area, we're going to say, let's call the area capital A. And we're going to say the area of this shaded region is found by taking the integral from, now we're integrating from 0 to 1. Remember, it was bounded on the left by the vertical line x equals 1 and the right by on the left by x equals 0 and on the right by x equals 1. So that means we're going to integrate from 0 to 1 of f of x minus g of x dx. So now let's go back and write in what those functions are. Well, we're given that f of x is x squared plus 2. So we'll say x squared plus 2, and then we're going to subtract from that g of x. So what is our function definition for g of x? Well, we're told that g of x is the opposite of x. So we're going to be subtracting, I'm going to go ahead and start some parentheses. We're going to be subtracting a negative x. And then don't forget your dx. Okay, so let's simplify that just a bit. Subtracting a negative x is the same thing as adding positive x. I'm also going to move the terms around a little bit so they're in order and decreasing powers of x. So that would be the integral from 0 to 1 of x squared plus x plus 2 dx. All right, so now what we're going to do is find the antiderivative. And if we take it term by term, the antiderivative of x squared is x to the third over 3. The antiderivative of x is x squared over 2. And the antiderivative of 2 is 2x. So we would have, let's see, x to the third over 3 plus x squared over 2 plus 2x. And we'll evaluate that antiderivative at 1 and at 0 and then subtract those two values. So if we first replace all the x's with positive 1, then we would have 1 to the third over 3 plus 1 squared over 2 plus 2 times 1. And then we're going to subtract from that the antiderivative evaluated at 0. So that would be 0 to the third over 3 plus 0 squared over 2 plus 2 times 0. And then at this point, we're done with calculus, aren't we? The rest of this would just be arithmetic. So I'm not going to spend a lot of time in this video doing the arithmetic. I hope you trust me if I tell you that the answer, the answer is 17/6. So this is equal to 17/6. That's just getting a like denominator and doing the arithmetic. So what does that mean? That means that 17/6 is the area below f of x, above g of x, and bounded by x equals 0 and x equals 1. Now let's take a look at example number 2 and see how it's like example 1 and how it's different from example 1. And so the directions say find the area between the two intersecting curves. So the way it's like number 1 is that we have a function f of x that would be our upper function, and then a function g of x that's the lower function, and we're finding the area between the two curves. But how it's different from example 1 is that this time, instead of being bounded on the left and by the right by vertical lines, our left boundary will be a point, this point of intersection, and then our right boundary is a point. So to find the boundaries, which would be our limits of integration, what we're going to do is we're going to take our two functions and we're going to set them equal to each other and solve for x. So I'm going to take 2 minus x squared and set that equal to x. Now this is a quadratic equation, so what we want to do is get it in standard form, and I want my my x squared term to be positive, so I'm going to move the x squared and the 2 over to the right, so it would look like this. 0 equals positive x squared plus the x that's already there, and then minus 2. And then we can solve this quadratic equation by factoring. So let's see, we're looking for factors of negative 2. I always look at this sign, which tells me that my signs have to be different. So factors of negative 2, so I'm going to put a plus and a minus that add up to positive 1. So factors of negative 2 that add up to positive 1 would be positive 2 and negative 1. Then that means our two solutions then are x equals negative 2 and x equals 1. So those are our bounds of integration. So now let's write an expression to find the area between the two curves. So let's see, I think I'm gonna do this curves over here. So to find the area between the two curves, we're going to take the integral from -2 to 1 of the upper function. Remember, the upper function is this f of x, which is 2 minus x squared. So that's going to be 2 minus x squared, and then minus the lower function, which is x. Let's put brackets around that and dx. All right, so we're ready to find the antiderivative then. And let's take it term by term. The antiderivative of 2 is 2x, and then minus x to the third over 3, and then minus x squared over 2, and we'll evaluate that from -2 to 1. So we'll first replace all the x's with 1, so that would be 2 times 1, minus 1 to the third over 3, and then minus 1 squared over 2. Let's put parentheses around that. And then we're going to subtract the antiderivative evaluated at -2. So that would be 2 times -2, and then minus -2 to the third over 3, and then minus -2 squared over 2. Close those parentheses. And then again, we're not going to take time in this video to do all the arithmetic, but if we did, our answer, let's see, would be 9/2. So now let's take another example of finding the area between two intersecting curves. This time though we have curves that are trig functions. So to find our bounds, again, we need to, our leftmost bound will be this point of intersection, and our rightmost bound will be this point of intersection. So to find those x values, let's set the two functions equal to each other. You can see that the upper function is the graph of f of x equals sine x, and then our lower function is the graph of g of x equals cosine x. So let's set those two expressions equal to each other. So sine x is equal to cosine x, all right? Now to solve that, let's divide both sides by cosine, and we would have sine x over cosine x is equal to 1, or in other words, tangent x is equal to 1. So to get our solutions, we need to find what x values between 0 and 2 pi, what x values give us a tangent of positive 1. So it might be helpful to take a look at the unit circle. So on the unit circle, where would tangent be equal to 1? Well, tangent is equal to 1 where sine and cosine are the same. So that would be at pi fourths, and then again at 5 pi over 4. Now the reason why we're going to pick those two is, remember in quadrant 1, well, I need to remember the sign of these trig functions in each quadrant. Everything is positive in quadrant 1, and then tangent only is positive in quadrant 3. So tangent x is equal to positive 1 when our angle is pi fourths, and then again at 5 pi over 4. So x is equal to pi fourths, and then at 5 pi over 4. Okay, so now we're ready to find the area between the two curves. So I'm going to scoot this over just a little bit. Okay, and to find the area between the two curves, our area would be the integral going from pi fourths, our lower limit of integration, to 5 pi over 4 of the upper function, which is sine x, minus the lower function, which is cosine x, and then dx. All right, so now let's find the antiderivative. The antiderivative of sine x is negative cosine x, and then minus the antiderivative of of cosine x is sine x. All right, and we'll evaluate that at 5 pi over 4 and at pi fourths, and then we'll subtract. So that would be equal to negative cosine 5 pi over 4 minus sine of 5 pi over 4. Let's go ahead and put parentheses around that, and then we're going to subtract the the antiderivative evaluated at pi fourths. So that would be negative cosine pi fourths and then minus sine pi fourths. Okay, so let's go ahead and evaluate those really quick. Cosine of 5 pi over 4 in quadrant 3, only tangent is positive. So let's see, the reference angle is pi fourths, and cosine of pi fourths is square root of 2 over 2. Is square root of 2 over 2. And let's see, we're taking the opposite of negative square root of 2 over 2. So that would be positive square root of 2 over 2. All right, and then minus sine of 5 pi over 4 is also sine of 5 pi over 4 over here is also, since tangent is positive there, sine is going to be negative. So we're going to be subtracting a negative square root of 2 over 2. So that is actually plus square root of 2 over 2. Okay, then minus, let's take the opposite of the cosine of pi fourths. So that would be negative square root of 2 over 2. Sorry about that. Negative square root of 2 over 2. And then minus sine, let's see, where are we? We're here. Minus sine of pi fourths, so that would be minus square root of 2 over 2. So minus square root of 2 over 2. And then let's simplify that. Let's just go ahead and simplify each set of parentheses. So this would be 2 square root of 2 over 2, and then minus, when we take negative square root of 2 over 2 minus another square root of 2 over 2, that would be negative square root of 2 over 2. Ooh. All right, so now subtracting this negative is the same thing as adding a positive. So we would get, oh, I'm missing a 2, aren't I? There's too many 2's. Okay, this should have been 2 times square root of 2 over 2. So when we combine like terms, we would get 4 times the square root of 2 over 2, which reduces to 2 square root of 2 for our final answer. Okay, so lots of arithmetic. All this stuff here is arithmetic. No, all this was arithmetic. Once we got to this point, we were done doing calculus, all right? So sometimes the hardest part is the arithmetic. Final answer, 2 square root of 2. Now in this next example, we're going to find the area between the curves that intersect in more than one point. So you'll notice that we actually have 2 areas that we're going to add together here. So when we look at the region from -2 to 0, you'll notice that g of x is less than or equal to f of x. In other words, from -2 to 0, the upper function is f of x and the lower function of g of x. Then after 0, it switches. Now f of x is less than or equal to g of x. In other words, g of x is our upper function and f of x is our lower function. So what we're going to have to do is write 2 integrals and add them together. So let's start with this left integral. We need to find our bounds of integration. So I need to find where the 2 functions intersect. So I need to find this point, and at the same time we'll go ahead and find this far right solution as well. So what we're going to do is set our 2 expressions equal to each other. So we're going to set 3x squared minus x squared minus 10x equal to negative x squared plus 2x. So let's go ahead and do that. So we'd have 3x to the third minus x squared minus 10x is equal to negative x squared plus 2x. All right, let's get that in standard form. So I'm going to go ahead and get the right side equal to 0. You'll notice that we have a negative x squared on both sides, so when I subtract that from both sides, they're going to cancel. And then we're going to subtract 2x from both sides. So we would end up with 3x to the third And then negative 10 minus 2 more would be minus 12x is equal to 0. All right, let's solve this by factoring. You'll notice that these two terms have a common factor of 3x. So let's factor that out. We'd have 3x times x squared minus 4 equals 0. So here we have a difference of two perfect squares, which will factor as 3x times x plus 2 times x minus 2 equals 0. So our three solutions would be x equals 0, x equals negative 2, and x equals positive 2. And I'm just going to go ahead and rearrange those with the smallest x value to the largest. So that would be x equals negative 2, x equals 0, and x equals positive 2. Okay, so now we're ready to write our expression to find the total area of the two regions. So we'll start with this region. So that's going to be the integral from negative 2 to 0. So from negative 2 to 0, we're going to take the upper function, which is f of x minus g of x. So I'm just going to go ahead and write this symbolically first. To find our area, we're going to start by taking the integral from negative 2 to 0. So from negative 2 to 0, upper function is f of x, lower function of g of x is g of x. So that's going to be f of x minus g of x dx. And then we're going to add to that, this second region. So this region. So now we're going to integrate from 0 to 2, but this time we're going to take our upper function g of x minus our lower function f of x. So that's going to be the integral from 0 to 2 of, need to turn it around and say g of x minus f of x dx. All right, so now let's go ahead and rewrite this, but we'll replace our function names with their actual function values. So let's go ahead and see if we can simplify when I take f of x minus g of x. So f of x minus g of x, we'd have 3x to the third. So 3x to the third. And then negative x squared minus a negative x squared. Well, those will just cancel. And then we have negative 10x minus 2 more x. So that's going to be minus 12x. Let's put brackets around that and complete that integral with a dx. And then we're going to add to that the integral from 0 to 2. So we're going to add this part of our g of x function minus the f of x function. So, well, this term doesn't have an x to the third term that you can see. It actually does. It's 0x to the third minus 3x to the third would give us negative 3x to the third. And then the x squared terms would cancel again. Negative x squared minus a negative x squared cancels. And then 2x minus 10x, or excuse me, 2x minus a negative 10x would be plus 12x. So this is plus 12x. Let's put brackets around that and dx. All right, so now let's find both antiderivatives. So the first antiderivative, we're going to take, let's see, this would be 3x to the fourth over 4. So 3x to the fourth over 4 minus 12x squared over 2 would give us 6x squared. That'll be evaluated from negative 2 to 0. And then plus, let's find the second antiderivative. So that's going to be, let's see, negative 3x to the fourth over 4. So negative 3x to the fourth over 4 plus 12x squared over 2 would give us 6x squared. And that gets evaluated at 0 and at 2. All right, so then that's going to be equal to, let's go ahead in this first antiderivative, we're going to replace x with 0 to begin with. So that would be, let's see, 3 times 0 to the fourth over 4 minus 6 times 0 squared minus, now we need to evaluate that at negative 2, so that would be 3 times negative 2 to the 4th over 4, and then minus 6 times negative 2 squared, okay? So all of that was this, okay? Now we need to add the second part. So that's going to be plus, I'm going to have to write down here, I'm going to evaluate our antiderivative at positive 2, so that would be negative 3 times 2 to the 4th over 4 plus 6 times 2 squared, and then minus, evaluate that same antiderivative at 0, so negative 3 times 0 to the 4th over 4 plus 6 times 0 squared. Okay, so I'm going to stop there. At this point, we've done all the calculus. The rest is just arithmetic, and I'm going to go ahead and give you that answer. It turns out to be positive 24. Nuts. What did I just do? And in this next example, it will be more efficient to integrate with respect to y, and I'll show you why in just a second. In other words, if f of y is the curve to the right and g of y is the curve to the left, so let's take a look at this graph. This curve on the right, here we have f of y is y plus 1. So notice this is a function of y instead of being a function of x. And then this line we can express, or I'm sorry, I had this backwards, didn't I? This curve is g of y, which is 3 minus y squared. This line as a function of y would be f of y equals y plus 1. Now, one thing I want you to notice is this time our representative rectangle is horizontal, isn't it? Okay, so as we think of an infinite number of rectangles, okay, they would all be horizontal, okay, and so these aren't great rectangles, and so that means our bounds, instead of being bounds that go from left to right, now we need to have bounds that go from bottom to top. So those will have to be y bounds. Okay, so if f of y is the curve to the right and g of y is the curve to the left, then the integral from, I'm going to use c and d this time instead of a and b, just to emphasize that c and d, these are y bounds instead of x bounds. So these are y bounds. So let's take the integral from c to d. And remember, f of y was the curve to the right, so that's going to be f of y minus g of y. And this time, since we're integrating with respect to y, we're not going to write dx, we're going to write dy. All right? So let's try this example where our rightmost curve is this curve g of y, and the leftmost curve is this curve. So to find the area between these two curves, first of all, even though we can actually read the graph and we can see what the bounds are, let's find these y bounds by setting these two equations equal to each other. So we're going to take y plus 1 and set it equal to 3 minus y squared. All right, and let's get this in standard form. I'm going to add y squared to both sides, and I'm going to subtract 3 from both sides. Then we're going to factor, and that's going to be y plus 2, y minus 1 equals 0. So our solutions are y equals negative 2 and y equals 1. Again, we already knew that by looking at the graph. Here's our lower y bound is negative 2 and our upper y bound is positive 1. So now we can write an expression for the area. So to find the area between the two curves, that's going to be the integral from, now let's use these y bounds, from negative 2 to 1 of the rightmost function. Now this time the rightmost function is g of y, okay, and g of y is 3 minus y squared. So this is going to be g minus y squared. I mean, not g, it should be 3. Sorry, let me fix that. Okay, this will be 3 minus y squared. 3 minus y squared, and then minus the left curve. Well, I mean, it's not a curve, it's a line. This left curve, which is y plus 1. And I'm going to put that in parentheses so we subtract the whole thing and not just the first term. All right, and then finish those brackets and don't forget your dy. Okay, so integrating with respect to y, you can use the same power rule as you do when you integrate with respect to x. So this would be the integral from -2 to 1 of, oh, you know, we can simplify this a bit. Let's go ahead and do that. I'm going to rewrite it with the y squared term first. So it's going to be -y squared and then minus y. And if we combine those constant terms, 3 minus 1 would be plus 2 dy. So now let's find the antiderivative. So that's going to be negative y to the third over 3 minus y squared over 2 plus 2y. Oops, I shouldn't have that integral symbol. Sorry about that. If we're integrating, I don't need the integral symbol anymore. But we're going to now evaluate that antiderivative from -2 to 1. So then we'd have negative 1 to the third over 3 minus 1 squared over 2 plus 2 times 1. Let's put that in parentheses, and then we're going to subtract from that the antiderivative evaluated at -2. So that would be negative 2 cubed over 3 minus, oh, I'm going to run out of room. Let me scoot over just a little bit. Minus -2 squared over 2 plus 2 times -2. Now, if you did the arithmetic, you should get 9/2. And we're not going to take the time to do all that arithmetic in class. As I mentioned earlier, once you get to this step, you're done doing calculus. Okay, so going from here to here, either on the AP exam, either you could leave your answer like that, or it would be a situation where you could use a calculator to get this answer. So what we're going to do now is we're going to take a look at this same problem, but done differently. Okay. So example 6 asks us to rewrite the equation of the curves in example 5 where x is a function of y. Then we're going to write the expression, but we're not going to evaluate it this time to find the area between the two curves. Now let me just go back to example 5 where we had that representative rectangle that was horizontal. Okay, one thing I want you to notice about a representative rectangle is that one end of the rectangle, or each end of the rectangle, should touch the two curves that you're finding the area between. Okay, so if we switch from a horizontal rectangle to a vertical rectangle, you'll notice when we do that, that this representative rectangle, well, if I were to draw several of them, okay, notice all of these have, we're touching both curves. Okay, until we get to here. Once we get to this point, if I kept drawing horizontal rectangles, notice now I don't touch each curve, I just touch the same curve twice. So what that means is I'm going to have to write two different integrals with respect to x. My first integral will integrate from -1 to here at +1, where we have this upper function, which is the line, minus the lower function. And then we're going to have to switch and write a second integral where we have this top half of function y minus this bottom half of function y. So let me show you what I mean. Well, let's start with rereading the directions. The first thing we need to do is rewrite the equations in terms where x is a function of y. So in other words, in the last example, we were told that f of y, which is the same thing as x, was equal to y plus 1. So if we solve that for y, subtract 1 from both sides, then y is equal to x minus 1. Okay? And then the second function, g of y, which we could call x, was equal to 3 minus y squared. So if we're going to solve that for y squared, I'm going to add y squared to both sides and subtract an x. So we'd have y squared equals 3 minus x. And then we'll take the square root of both sides. So y is equal to plus or minus the square root of 3 minus x. The positive square root of 3 minus x is this part of the curve, and then this negative square root of 3 minus x is this part of the curve. Okay, so to find this total area, we're going to write two integrals. Now, luckily this time all we have to do is write the expression. We don't need to evaluate it. So to find the area between those two curves, we're going to first integrate from, now this left bound, as we go from here to here, our left bound is -1, and then we'll stop right here when we get to 2. So from -1 to 2, we will be taking this function, this linear function, minus this function. Okay, so we're going to integrate from -1 to 2. We're going to take the top function, which is x minus 1, and subtract from that the bottom function. Now, this bottom function is this, when you're below the x-axis, that's the negative square root of 3 minus x. So we're going to be subtracting a negative square root of 3 minus x. Okay, and close those brackets, and don't forget the dx. And then we need to add to that the second part. So we've already integrated from -1 to 2. So the second integral will integrate from 2 to this right bound. Now we need to figure out what this x value is. So what is the x value? This is where y is equal to 0. So what x would make this expression equal to 0? Well, if x were 3, because 3 minus 3 is 0, and the square root of 0 is 0. So we need to add the integral from, pick it back up at 2 to 3, of the top part, let's see, this top part of the function minus the bottom part of the function. So that would be the square root of 3 minus x. So the square root of 3 minus x, and then minus the bottom part, which is this part. So that is negative square root of 3x. So we're subtracting a negative square root of 3 minus x. Okay, close parentheses. Let's put brackets around all that, and then don't forget your dx. All right, so we're not going to do all this find these integrals and evaluate, but if we did, we would end up with this would be equal to 9/2, which was the same answer that we got in the last example. Okay, so I just want to point out that when you have a situation where you have a rightmost curve, you have a rightmost curve and a leftmost curve, it's going to be a whole lot easier to integrate in terms of y. As you saw down here, it is possible to integrate in terms of x, which we did, but it was a lot clunkier. So it would be a lot better to integrate in terms of y. Okay, so you can go ahead and get started on your homework if you want, and if you have any questions, be sure to ask me in class.